Hi everyone and welcome to the internet. What we're going to be doing in today's lesson is having a look at the periodic table. So obviously this is something you're quite familiar with from chemistry for many years I expect, but we're going to be having a look at it, so hopefully by the end of this lesson you're going to be able to describe the development of the periodic table and explain the different patterns that we've got within it. To start off though, we've got 3 questions based around our previous lesson. So have a go at answering those 3 questions in your books for me. Let's double check our answers then. As always, tick any you've got right and make any corrections that you need to. So question 1, we've got 3 marks available to us here. So the first mark is if you said positive metal ions. Second mark for saying they're surrounded by delocalized electrons. Now you could have got those 2 marks from a label diagram like the one in the bottom right, but you needed to have positive metal ions and delocalized electrons labelled to get those 2 marks. The third mark is for saying that the metallic bond is the electrostatic force of attraction between the delocalized electrons and the positive metal ions. Question 2, at room temperature most metals are solid, 1 mark, and if you picked up on the exception of mercury being a liquid, you get a 2nd mark there. Then the final one, in terms of our structure, then it's giant because many ions are present in the structure, and a second mark for saying it's a lattice because they're in a regular pattern. So that's a total of 7 marks for today. So add up your scores out of 7 and write your total in your book. If we think about the periodic table that we know today, then this wasn't something that popped up overnight. It was actually the result of a lot of work by various scientists over the years. And the key person that we attribute to our modern periodic table is a Russian guy called Dmitry Mendeleev. Now, his periodic table formed the basis for our modern one. And what he did was a little bit different to what some of the others before him had done. He considered 3 key bits of evidence. The first one were the atomic weights of the known elements. The second piece of evidence was knowledge of the chemical reactions of different elements. And the third one were the knowledge of the physical properties of the different elements. And what he did, when he had all of that evidence, he then started to arrange the elements into his version of the periodic table. So jot those points down for me first of all, and then we'll have a look at what he did in more detail. It wasn't a case of he woke up one day and then he put this all together, first time, got it spot on. He went through a range of techniques, strategies, trials to actually get to the one that he finally settled on. Because when he started to arrange the elements, he started off with his groups being organised as rows. But then he later decided that actually he wanted the groups into the columns. And hopefully that sounds familiar to us, because if we think about the modern periodic table, the groups are in those vertical columns. He also, when he was arranging these elements, because he was looking at their reactions and their properties, every once in a while as he got to them, he thought, well, actually, this one doesn't really fit in the next gap we've got. What we need is it to move one step to the right. So what he actually had the courage to do was he felt that there were elements that hadn't been discovered yet. So he left gaps and suggested that actually that gap will be occupied by an element that's got similar properties to the others in the group that we just haven't found yet. And he gave these elements that hadn't been discovered yet names like Eka aluminium. And the other thing he did that was very important was he found that tellurium and iodine didn't really fit based on their atomic weight. So what he decided to do was swap them round. So what he did was he based that on their properties. So what we see is, firstly, he put our elements into groups which were columns. He left gaps for elements that he didn't think had been discovered yet, and then he swapped some of them based purely on their atomic weight. They would have arranged in a different order, but looking at their properties, he wanted them the other way around, like tellurium and iodine. So jot those points down in your summary. Now, this is what the periodic table that he created looked like. So you can see there that it's the one that he created in 1871. Now, what we can see, we do have our groups at the top, so that's as we expect it to be. So our groups are these columns that we have. And if we look at that first column on the left-hand side, we've got hydrogen, lithium, then we've got nitrogen and potassium, rubidium. So we can see that there's actually some of them that we still associate with group 1 in there today. And you'll see that there are some that we see in group 2 are in the group 2 column, and so on. So that was what the periodic table looked like initially. If you remember, we said that one of the things that he did was he worked out that there must be elements that hadn't been discovered yet, and he gave them names like eka-aluminium. Now, when these new elements were eventually discovered years later, then he'd already predicted their properties, because what he'd done by organising the elements into those groups based on their reactions, their properties, he could then say, well, that gap is going to be something that has the following properties. And in the table at the bottom there, you can see what we've actually got are different properties down the left-hand side. And then we've got what he predicted for 2 different elements, so eka-aluminium and eka-silicon. And then what the elements actually did have when we discovered them. So eka-aluminium we know as gallium, and eka-silicon we know as germanium. So if we just look at the eka-aluminium and the gallium, then he predicted that eka-aluminium would have an atomic mass of 68, and gallium's actual mass is 69.7, which is pretty close, let's be honest. If we look at the density, he predicted 5.9, and it's actually 5.94, so it was 0.04 grams per centimetre cubed out. He said it would have a low melting point, and it does at only 30.2 degrees Celsius. He predicted that the formula when it joins with chlorine would be EaCl3, so each eka-aluminium will join with 3 chlorines, and it does. And the formula of the oxide, 2 of those would join with 3 oxygens, and it does. So we can see that by studying these other elements that we'd already discovered, we could predict the properties of the one we hadn't yet discovered. One of the key things that we've got to remember is that when Mendeleev was doing his periodic table, he was organising them by the atomic weights. Now, the reason he did that was because during his lifetime, we didn't know the atomic number. So that was something that came much later in 1913 when a scientist called Moseley discovered that the atomic number was the number of protons in the nucleus. And the great thing about the work that Moseley did there was when we then looked at the number of protons, so the atomic numbers, for each of the elements on the periodic table, it proved what Mendeleev had done was right. So where he'd swapped those elements, it was exactly the right thing to do, because even though the atomic weights were different, then the atomic numbers counted up sequentially. And if we think about the periodic table we use today, it's by the atomic number. It goes up. Start on the top left and you've got 1. Across to helium is 2, back to lithium, 3, and so on. When we get to 1894, then we've got another scientist called Ramsay, and he actually discovered an element called argon. Now, this was an element that nobody had predicted existed at all. And the year after that, he discovered helium. So, thinking about what we know, why do we think that nobody had predicted argon or helium existed? hopefully what we were able to do was, looking at our periodic tables, you'd notice that those two elements are in group 0 on the far right hand side. Now, because they're in group 0, they're both inert, okay? That means they're unreactive. And what we already knew from the way that Mendeleev had structured his periodic table based on the reactions, he thought that elements should be able to react with other elements. And we know that those elements in group 0 aren't reactive. They don't really react with anything. So therefore, he didn't think that they existed because they didn't carry out these reactions. So the reason nobody predicted they existed was because the gases are inert, and they thought that elements should be able to react with other elements. By 1898, we discovered another 3 elements: neon, krypton, and xenon. So Ramsay actually suggested to Mendeleev that these gases should be placed into a new group that was going to be placed to the right of group 7. So what we have here is an example of where scientists were collaborating with their own individual studies that then fed into one bigger idea. So while obviously these two scientists were working individually, because their ideas were centered around the same thing, then they were able to share their thoughts with one another to then develop the overall picture. So let's see what we remember from looking at the periodic table further down the school. What patterns do we have on the periodic table? Write down any patterns you can think of at all. Firstly, our modern periodic table, the elements were arranged in order of increasing atomic number, which is how it moves away from those early versions of the periodic table which were always arranged by the atomic mass. Secondly, the atomic number is the number of protons in an atom, so just by looking at that number on our periodic table, we know the number of protons that are in any atom on the periodic table. We know that the number of protons is the same as the number of electrons within an atom. Think back to our structure of the atom diagrams we did in our earlier chemistry topic. We know that the electronic structure of an individual atom is determined by the number of electrons, and the electronic structure then tells us the chemical properties, because remember, the number of electrons in the outer shell is then going to determine how things react, and how many shells they've got tells you about their reactivity as well. So jot those points down if you haven't already got them all. Any you've got, give yourself a tick. One of the things that I think is very helpful to do on your periodic tables you've got stuck in your books is to just remind yourself by writing the charges that you get on the ions for each group at the top. So where it's group 1, they will always form +1 ions. Group 2, +2 ions. Group 3, +3 ions. Then we can jump across to the right hand side, and if they're in group 5, they form -3 ions. Group 6, -2 ions, and group 7, -1 ions. So you can add that to the top of your periodic table as a quick reminder of how we know the charges on those ions. The rest of the table here just summarises a few of those key patterns that we've got, looking at 4 key groups that we're going to study in a lot more detail in one of our later chemistry topics. So groups 1, 2, 7 and 0. First of all, groups 1 and 2, they're on the left hand side, which means they're both metals, whereas groups 7 and 0, right hand side, they're non-metals. If we think about the reactivity, group 1 are the very reactive ones, and you're going to study a lot more of that in C4, and group 7 are also very reactive, whereas group 2 is reactive and group 0 is unreactive. Then in terms of the electronic structure, our group 1s always end in 1, group 2s end in 2, group 7 ends in 7, and group 0, the outer shell is full. So whatever the number of electrons the outer shell can hold, that's how many it has. And then we've already talked about the ions. So that's a really quick guide for you on some of the patterns that we can have. Final thing for today then are the plenary questions. So those of you with target grades up to grade 5, 2 columns on the left, target grades over at grade 5, the 2 columns on the right. And I would also suggest that you do the extension task there to create yourself a single page summary about the periodic table and the different types of bonding that we've encountered throughout C2. Because what we've actually done is we've finished almost a section of C2, if you like, looking at all those different types of bonding. And then for the last part of this, we're going to be having a look at things like carbon and so on. So this is a good point to do a quick single page mind map summary, something that just ties all of those ideas together in a simple, quick, one-page review or summary. I'll leave this up for a couple of minutes today, but as always, if you need longer, hit pause and take as long as you need to answer the questions.